This video is going to continue looking at ester enolates and Claisen condensations. We can also make beta-dicarbonyl compounds into nucleophiles. So same chemistry as our last video. We're still going to be able to take that alpha hydrogen off pretty easily, considering it's in between two carbonyl compounds. At this point, we can make this into an anion, into a nucleophile, and have it kick off any halogen from an alkyl halide, and another way to make a new carbon-carbon bond. If you have two hydrogens, you can use a stronger base and add a fourth substituent. So here we have no more alpha hydrogens, but we've added two new carbon-carbon bonds here. You can also undergo simple reactions. Doesn't matter what the substituents are as far as what's on either side. This is a diester that still will allow you to add a new carbon-carbon bond while keeping that last hydrogen available for another connection. If we use water with a dicarbonyl compound, you should remember that water hydrolysis of esters gives us acids. These acids that form with beta-dicarbonyl compounds allows for decarboxylation. So if you had an ester in a beta-dicarbonyl product, you'd end up getting a ketone. If you had a diester, you would end up getting an acid. Let's go through this mechanism. So our mechanism is going to start by pulling off one of those hydrogens with a strong base, creating a new carbon-carbon bond. We're going to represent that as a Cr bond. At this point, this should remind you of our carboxylic acid derivatives chapter. Acid water workup with a diester is going to turn that into a diacid. Now, I have this here in brackets because it is not able to be recovered. It is an intermediate. But I like to show you that it's forming so you can see how we're going to lose one of these carbons. This should remind you of the stuff we worked on in the last video. We're going to have a 6-electron or a 3-arrow transition state where our carbonyl grabs that arrow, electrons push down onto that carbon. There's your CO2. We've now made an enol, which can tautomerize into a ketone, into our acid here, with carbon dioxide being lost as a gas. Now this is going to happen due to the transition state, and remember here that not every carboxylic acid will do this. It will only be ones that have a beta carbonyl in that position to allow for this transition state. So even if you have a diacid, you will not lose both. You'll only lose one of them. The other thing we can do with beta dicarbonyls is we end up turning them into nucleophiles with unsaturated carbonyl compounds. This is known as the Michael reaction, or a Michael addition, where we have 1,4 addition, 1 being the oxygen, 4 being our beta carbon of our alpha beta unsaturated double bond. If we use base, it's going to pull off one of those alpha hydrogens. That carbon will become nucleophilic, move over the double bond, and we now have a new carbon-carbon bond. That molecule on the left is an ester. It's just written in an unusual way. That is the same ester we've worked on previously. So let's talk a little bit about the Michael acceptor. It can favor 1,4 addition, and the reason why is because those carbons are going to be your most electrophilic. 1,4 versus 1,2. So we will have a positive charge on our carbonyl carbon and a positive charge on our beta carbon. If we have a nucleophile that attacks at our carbonyl carbon, our electrons from the oxygen can still push that group out. So 1,4 is going to be favored, even though you will see some 1,2 in low amounts. For a mechanism, we can have our nucleophile, again, whatever beta dicarbonyl compound you're starting with, as long as it has at least one alpha hydrogen available, will come in, attack at the beta end of your double bond, pushing electrons out towards the oxygen. We can have this pick up a hydrogen. Here we now have our enol, which again can tautomerize into its keto form, which is our ketone. And again, 1,2 will occur, but thermodynamics will not allow it to form in very large amounts. The Robinson annulation is one famous way to utilize the Michael addition. Here we have our alpha beta unsaturated carbonyl. This would be methylvinyl ketone, that's the MVK. On our left, we have our carbonyl compound that's going to involve pulling off that hydrogen at the alpha position and turning that into our nucleophile. So we'll end up seeing are add the new carbon-carbon bond as well as enclose the ring, which is what makes this very useful. So a Michael reaction plus an intermolecular aldol will end up giving us a conjugated cyclohexanone. It'll start by pulling off this first hydrogen. We can then turn that into a nucleophile, remember pushing your electrons from the double bond to our carbonyl carbon and electrons out onto that oxygen. At this point, that O-, when it drops back down, it can pick up your hydrogen off of a water molecule. This is essentially your enolate ion undergoing our keto-enol tautomerism, going to our ketone. So remember our positions, alpha position would be our methyl group off the ring, so beta, gamma, delta. This would be known as a delta diketone. From here, remember that we're eventually going to close this ring. So the easiest way to make that new bond is going to involve taking one of those alpha hydrogens off that methyl group and then having that attack as a nucleophile, again at the carbonyl on our original ring. So we'll pull off that first hydrogen, have that act as a nucleophile, break that carbonyl bond, and then again also picking up a hydrogen from available water. At this point, the only thing missing is our level of unsaturation. So here we can pull off a hydrogen from that alpha position again, kick out our OH. Remember, we're under basic conditions, so that will allow our OH to leave as a leaving group without it being protonated. And if you look at our final product, you can see that we have a conjugated cyclohexanone, so another advantage of why that OH leaving is preferred. And this is your end product. That's it for this video.